From South Bend, Indiana, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
We're talking to large OEMs and they're saying, hey, I have a fleet of 65 machines and I've got all these operators and everything like that. It's okay if the things are strong enough now, but it takes me 20 hours to print it. So it's like, if I can cut half of that print time, I am over the moon. They're like, I don't care about material savings. I don't care about the weight savings. I don't even care about the performance of the end part because it's close enough.
That was Aaron Chow, co-founder and CEO of Vixiv, a startup transforming how we design and test 3D printed parts using AI. With a background in electrical engineering and years of hands-on AM experience, Aaron is leading the charge in lattice optimization, turning real-world failure data into better, faster designs. Based in Cincinnati, his team is rethinking the digital workflow from design through validation. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. You can find the show on Spotify, Apple, Amazon, or wherever you get your podcasts. If your team needs help with materials qualification, AM strategy, or wants to learn more about our digital data management tool, Trace AM, reach out at info@3degreescompany.com.
All right, Aaron, thank you so much for joining the show today. Excited to hear what you're up to and kind of how you've gotten here. But before we start, or kind of as we start, I really like to start to get a sense of the person. So where were you born? Where'd you grow up? Do you have a formative engineering or technical memory that you'd like to share with our listeners?
Yeah, thanks for having me today, Mike. Great question. Born and raised here in Cincinnati, Ohio, where actually my business is based now. I first actually cut my teeth on additive kind of backwards from everybody else. My first real in-depth work was with GE Aviation here in Cincinnati. So a lot of people remember that GE published a lot of information saying, hey, 3D printing is incredible. We're doing this amazing work on the jet engines here. I was fortunate enough to get to actually see that and be part of the teams that were working on that back in 2014, right here in Cincinnati. That's where I met a bunch of really smart people doing a bunch of really cool work. And that's also where I was kind of dumped directly into metal 3D printing. This was at the same time of like the wooden MakerBot replicators were the ones that were like generally available, and they were starting to come out with the steel frame ones. So it was really, really interesting kind of seeing what everybody was saying about these desktop printers and everything like that, and then going into work on, $1 million metal machines, old EOS machines, concept laser machines, and some RCAMs. So born and raised in Cincinnati, was actually fortunate enough to work for GE in high school, and then went to college at University of Michigan, studied electrical engineering, but still did additive pretty much every single year, both during the school year and during the summers. I was fortunate enough to get a lot of great experience with everybody from, starting with GE, moved to Ethicon doing laparoscopic surgical tools with them, did some work with Diffuse Synthes on their surgical implants, and then went through with a lot of other fun people doing a lot of other fun projects, but kind of landed at Autodesk out in San Francisco. So got to spend some time at their HQ on One Market, and then also at their Pure 9 facility right on the water, where I got to design and build a lot of cool stuff.
And so do you remember, when was the first time that you saw 3D printing?
So the first big dip into 3D printing that I saw was, it was a little chess set, or it was a little rook from a chess set with a DNA helix on Greg Morris's somewhere desk. Over here. Yeah, exactly. It was a little metal one on Greg Morris's desk at GE. So my boss at GE was like, hey, you need to meet this guy. They're doing this really cool technology stuff. And this was just one of the little demo parts that he had sitting on his desk. But I remember that real clearly. It's very similar to the one that Formlabs was using for a while. But it's that little...
It's got the staircase and the helix in it.
Yeah, staircase with the DNA helix inside.
Yep. So talk a little bit more about kind of the internship that you did during high school. That's pretty interesting. Was that through like... How did that come up? What were you doing, and kind of how did it kind of shape some of your career thoughts?
So that was a really interesting thing, because that was actually through a program in Cincinnati called Inter-Alliance. And essentially what it is kind of the early to mid 2000s, Cincinnati was seeing a huge brain drain. Is the same thing that was happening to a lot of the Rust Belt towns, where it was just anybody who was really good left. And it was really bad for all of the big companies here. And kind of what people don't realize about Cincinnati is it's kind of a sleeper city in a lot of different ways. So, first off, headquarters of a huge number of Fortune 500s are here. So Kroger is headquartered here. Procter and Gamble is from Cincinnati. GE Aviation headquarters is in Cincinnati. Great American Insurance, Fifth Third Bank. So there are some humongous names here that are kind of spread across financial, manufacturing, and technology that people don't realize are actually in Cincinnati. Those companies are all losing talent to the coasts and other places just because of, people's perception of a Midwest town and all of this stuff. So they have been investing a lot of money into trying to retain these talent pools, both in attracting new talent by making the city nicer, bringing in more, small shops and small businesses and things like that, revitalizing the downtown. But also, the program that I was a part of, which was how do we retain the talent that we already have, or hope that they come back after, maybe going somewhere and getting additional experience. So that program was really interesting because it directly connects high school students with these Fortune 500 companies. And, it's pretty crazy because you look at the resumes of the kids who go through these programs and they're like, junior in high school, they worked for P&G doing manufacturing line work.
Right.
And it's just like, it's ridiculous the opportunities that they give us in order to try and do this stuff. And I think it really helps both in, university applications for just getting to some of these other places. It's helpful to have that and have that experience, but it's also, I think, really helpful in discovering what you actually want to do, because at the end of the day, let's say you want to do some manufacturing engineering. Doing that in high school versus like going on a shop floor at GE and seeing how the engines are being made are two very different things. Mm-hmm. And being able to see some of that stuff, I think, has the opportunity to guide some of these students towards fields they may never have heard of or may never have been interested in for whatever reason, just kind of by showing the possibilities that are out there. Especially, when I was in high school, I graduated in 2015. None of my classmates were like, I want to go into manufacturing, literally zero of them. So, the question is there, valuable work there? Is there really interesting stuff for certain people? And then how do we actually connect those people up with that work? And programs like the one that I was in was just like, how do you get into GE's shop floor as a high schooler? There's literally no way. So that was just a great opportunity.
And it seemed to work in your case, right? You went out to the coast and you came back.
100% worked in my case. So it was, manufacturing. My journey was manufacturing floor at GE. Then I was working IT for Kroger. So I did the essentially some customer service stuff where we wrote a bunch of scripts to help out with that. Then Med Devices, which was also Cincinnati. Then I was in Miami, Florida doing 3D printing. Then I was in San Francisco. Then I was in India, and then, kind of all over the place.
And with that experience, it's a journey in geographies. It's kind of mostly around the same industry, I would say, kind of additive stuff and some software. A lot of big companies, but now you're kind of running your own kind of small business. So talk to me a little bit more about kind of what are some of the things that you observed working with a big company and then kind of that puts you on that path. Because I think similar to your internship kind of discussion that just came up, I've always viewed internships as just as valuable of finding what you like to do. It's also getting insight on what you don't like, right? Some people don't like big companies. Some people want big companies. Some people want access to a bunch of different machines or a few or leadership in different ways. So from your kind of personal perspective, like what were some of the key takeaways that you've collected along this, along these different stops?
Yeah. So the way that you phrase that of, finding the things that you like and also the things that you don't like is something that I real strongly believe in. My thinking with internships and especially contract work with these companies is it's a great opportunity to try a bunch of new stuff without being locked in for years. Specifically with the internships, it's good because it's like you don't even need to sign a long lease or something. Like you can just say like, a lot of those are over the summer, so you can just reach out to the local university and like stay in the dorms for super cheap. Like that's what I did every year. It was hilarious. I met some great people there, but it was also like, I didn't have to get a lease, didn't have to get any furniture, didn't have to do anything like that. I will say my time at GE, I had an absolutely fantastic time. Loved the big organization. I actually liked the kind of rigid corporate stuff that was happening. Some of the stuff was a little bit of a pain in the butt because things were just moving slowly because, you have to get through approvals and you have to talk to different people and all of that. But I really enjoyed that. And I think it was a great foundation for learning. It was really interesting, though, because I actually got a return offer for GE and I went to Kroger. So literally exactly as you were saying, it was, let's try something new while I'm only locked in for a 3-month contract. Let's go give it a go and see if I love it or see if I hate it. Just try something entirely new. And that's really what it was, bouncing around with everybody. It was always kind of centered around manufacturing, specifically advanced manufacturing, and what can we do with additive that we couldn't do anywhere else. And it's really, I deliberately stayed away from the machine OEMs. So my goal was never to sell a machine. My goal was always, how do we solve a problem? And in the event that we need that machine, we'll go use that machine. But I was never trying to fit a square peg in a round hole. So the other piece of that kind of that I learned was it was really awesome working for all those big companies because it's a lot of resources and it's a lot of smart people. And sort of what came out of that was, really for the last 11 years, it's been awesome to see what those companies are pumping out. But it's really frustrating to see that it's not getting any further than that. So GE says, hey, we built this amazing thing. It's incredible. It's fantastic. We'll put it into production. Autodesk will write some great story. Automotive OEMs will write something. But then you look at all the people that are manufacturing stuff, and none of those ones are the ones able to actually tackle that technology and make it really work for them. And it's
what do you mean by that? Like the smaller companies in general, or what do you mean by like it's getting stuck in?
Yeah,
innovation's getting stuck in the big companies, or is it something different than that?
Yeah, a lot of the small companies just can't access it. So it's really interesting because, working at GE, it's like, hey, here's 24 engineers, 3 dozen engineers, here's $2 million and, 2 years to work on this, go nuts. And those smart people can produce a lot of great stuff. But the problem is, these smaller organizations that are, I hesitate to say less sophisticated, but maybe have less access to resources, are not able to implement some of those solutions. So GE says, hey, we made this thing 50% lighter. But what's not said in the news release is, oh, it took us 10 engineers and $2 million. And then it's like, okay, well, of course you can make it lighter. But then, all these other guys are out there saying, hey, I would love to make my product lighter, right? I could see it making it better for the customer. I could decrease logistical costs. I could decrease the manufacturing time and cost, and I could decrease my waste. That sounds great. How do I do it? And that's really where everybody gets stuck. That was really the driving force behind building this instead of taking any of my job offers with any of the companies out of college. It was, you guys are doing sweet stuff, but man, there's a lot of people out there that could really benefit from it that are just a couple steps away, and we might be able to bridge that gap.
Yeah, along those lines, I mean, we're just kicking off some work similar in that vein in South Bend, like a region similar probably to Cincinnati, a lot of manufacturers, small manufacturers. Like if you were king of the world for a day, what is your solution to kind of bring some of these smaller manufacturers up to speed with additive? Is it just money? Like, hey, I'm going to give you $1 million and you get to buy a machine and you hire an engineer for 3 years? Or is it what in your mind would move the needle the most?
So that it's going to turn into a little bit of shilling for what we're building here, but
that's the art of the question. That's the art of the question.
Sort of the background.
Take the softball.
The background question of that becomes, all of these other items and why they wouldn't work. So the top question is the machines, right? You go to all of these shows, these OEMs say, hey, look at this amazing thing I can make, right? And then you're looking at the part and you're like, okay, but it's not like I had that design sitting around and I was like, I just can't make it. So that's the first problem is even if you give away the machines for free, that doesn't solve the problem. The second problem is the money, right? Let's say you're able to get X dollars to go hire these engineers. Well, there's not that many of these engineers that can design it around, and those engineers are getting snapped up by these big organizations. If an engineer is sitting there looking at an offer from you and an offer from GE for $300,000 to go do this, which one do you think they're going to take? I mean, any reasonable person is not going to come work for you in your small company with your stuff. So that's really where we think that we can bridge the gap with our tools is we are actually building predictive models that allow you to do all of this at this point in time, lightweighting and latticing, that the bigger companies can do with an army of engineers, tons of time and tons of money. Now, our vision with this is similar to how CAD replaced drafting tables. You can take a lot of smart people and give them essentially a better tool, and that really saves us on two ends. So one is you're a small manufacturer doing your thing. Me, specifically, I can pretty much guarantee that you know more about your industry than I do. So it's kind of a waste of time for you to come ask me and try to tell me, oh, here's what we're designing, here's the pitfalls. I'll come back with a design. You say, oh, there's 3 more things I forgot to tell you about. That's going to, it needs to be implantable. It needs to be some certified material. It needs to be some certified process. And, the back and forth is sort of a waste of time because it's, you already know the stuff in your head. Why don't I just give you my calculator instead of you trying to train me? And that's what we're trying to do here is how can we quickly cut through the noise and present the users with a set of solutions that they can actually work with, but not make decisions for them. So I can give you 10 different solutions in 5 minutes that say, hey, do you want it to be super light? Do you want it to be super strong? Do you want it to be made out of this specific material? Do you want it to be, whatever this is? I'll present you all those solutions. And then from there, you can make the decision with your industry knowledge. And that's where I think the problem comes in is we talk to engineers all day long. They don't care what the lattice is. Lattice A, B, C, thickness A, B, C, material A, B, C, doesn't make a difference. They say, does it work? Can I produce it at volume and at the cost that I need it? Those are the only 2 questions. So like when the additive guys are talking about latticing and they're like, oh, this special auxetic structure or this special, high compression or good for impact absorption or something like that. And then you say, here's the 50 parameters that we tune in order to get there. Most engineers that are looking at direct applications don't care about any of it. They're like, couldn't care less if it was a big or small shape or a thick or thin beam. Just tell me if it does its job. And then it inevitably gets into the conversation of, well, I can't tell you what it's going to do until we build it and test it or simulate it or, something.
So let's take a step back and maybe just talk about kind of the origin of the company and kind of what it is that you guys, described a little bit of what you guys do, but like tell us about the team, like what are you doing, kind of where you are at the stage of kind of building the company.
Yeah, so one piece on the product side, just to kind of give a nice overview. Essentially, the problem that we're trying to solve is the same problem that gives additive its power. With a potential infinite number of shapes that you could print, there's theoretically a really great solution for whatever you're working on. The problem is, with that potential infinite number of shapes, you have essentially a 0% chance of actually finding it. So that's really the very high level question that we answer. How do we dig through infinity to find the solutions that'll do your job really well? We're a super small startup here. We've raised 2 financing rounds for a total of 5.3 million so far. And those 2 financing rounds have gone all into building facilities and products here in Cincinnati. What that looks like today is a total of 8 team members, all here on site. And then we've got a small production lab where we're actually building data in order to train our machine learning models. So it's a super small team. We've got a couple guys running in the lab, a couple of guys running technical development, and then a few others that are kind of working with customers and working on bugs and things like that. And really what it looks like for us is, our approach kind of differs here because we build physical parts. We then actually will destructively test those physical parts, and we'll use that data to feed our AI model. So that enables us to have really, really clean data sets. And it also allows us to actually guarantee a lot of these results because we can guarantee the process by which it was trained.
And so 2 questions on that. What kind of machines are you guys producing parts on? And then how do you destructively test them? Those parts.
That's a good question. So
the materials engineer coming out of me.
So we're running an HP 5200, just running nylon 12. And again, the goal of that is it's pretty accessible to anybody, in the sense of if you're a big company, you can go buy them from HP. And if you're a small company, you can have somebody contract manufacture these parts. And there's plenty of contract manufacturers, plenty of these floating around. Again, that goal with this first models that we're building is prove that it'll actually work for a bunch of customers who want to try things. We can work on the niche things later. Let's work on the overarching umbrella. The testing side of things, I mentioned briefly, what we're doing right now is just static loading. So we say, hey, with a lattice structure, how much weight can it hold? There's a ton of different parameters. It gets way more complicated than that, but that's it getting boiled down. Right now, what that's looking like is just using a load frame. So we're actually using the Frank Bacon load frame up in Michigan is where they're actually produced. And we're actually just crushing the parts. So we're analyzing those stress strain curves and then inputting that back into our model to say an object with all of these parameters has this stress strain curve. And then that's what allows us to predict unknown curves for unknown shapes.
Got it. And where do you think, so you mentioned lightweighting and some other applications, but if I'm an end user or if I'm a person kind of developing a part or having to manufacture a part for an OEM or something like that, like where do you expect or where do you see the kind of those people kind of coming to you? Like at what stage is it? Is like, hey, like I've got a small volume order. I want to maximize as much kind of cost savings as I can by removing material or lightweighting, or like where do you envision some of the kind of those initial use cases being? Is it a particular industry? Is it a particular kind of core part or core kind of functionality that you have in mind?
Yeah, so that's a great question. That's the one I've been wrestling with as well. The very short term is the tool makes things lightweight and keeps the strength. And the initial actual prediction for where that would be useful would be for the folks who are looking for higher performance on their parts. They say, hey, if this part is lighter, my boat goes faster, or something like that. Pretty direct translation of that. What we've been finding actually talking to customers, though, is it's kind of interesting. A lot of the ones that are really excited about what we're doing don't care about the performance. So the cascade is really three pieces here. You have the performance of your part. You have the decreased logistical costs just due to the part weighing less. And then you have the decreased manufacturing costs, both in time and money, because you're just making less of a part. And it's really interesting because that third piece is where everybody seems excited. We're talking to large OEMs and they're saying, hey, I have a fleet of 65 machines and I've got all these operators and everything like that. It's okay if the things are strong enough now, but it takes me 20 hours to print it. So it's like, if I can cut half of that print time, I am over the moon. They're like, I don't care about material savings. I don't care about the weight savings. I don't even care about the performance of the end part because it's close enough. But if I can cut all of that printing time, then that makes a really, really big difference. That's where we're seeing traction now. And those are the customers that we're kind of directly supporting. And it does kind of make sense when you step back and look at it, because those are a lot of the ones that are not really being targeted or supported by the existing processes. So, giant printer OEM, of course they want to do the part for the spaceship, right? Like, that's a great story. You don't want to be like, oh, I fixed this leg for a conveyor belt. Like, which one's going to write you a better marketing story? But those guys, we were talking to some that were just like, hey, we have to repair this part every Monday, which is like kind of fine, but also, corporate won't send us an engineer to redesign it. So we just have to reprint this part and do it every time. It would be great if we could do it faster. And it's just like, let's reduce operator load. Let's reduce the speed on the usage of the machines and increase the throughput so we can, get more out of our labs.
And so you guys are at kind of a development stage now, gathering lots of data, kind of feeding the AI and machine learning models. What do you envision as the workflow as the technology matures? Like, do people come to you and it's kind of bespoke and like, hey, there's a little bit of discussion? Are they dropping in a file and then clicking these three buttons? Like, what does that look like?
Yeah, so that's a great question. And, on the development scale side of things, really what we're looking at is probably to have enough of a tool for release by the end of June. And the hope for that is I'm attempting to cut myself out of the equation. So what my dream would be is essentially a tool that people will be able to access and then be able to actually use to be able to input their parts and then get out that host of answers whenever they want them on demand. And hey, we need to make a design change or a revision, rerun it 5 minutes later, you get those answers. The real big goal of all of this is I want to put this power into everybody else's hands. There's different models, a lot of different business models for all of this. But my question is, if we want to affect the most change and get this benefit into everybody's hands, we need to just get that tool out there. We can't say, hey, you need a consultation, you need, 10 hours, sure, you need this other thing, you need all this stuff up front. No, that's just causing a lot of barriers to adoption for all of this technology. And that's why we want to try and get it out as a platform that essentially is accessible, that we'll be able to get users on and be successful with quickly. Kind of the other piece of that question is, where does this fit in the workflow? So we say, hey, we're gonna add a new software tool, right? Everybody starts shaking in their boots for one reason or another. You got the CAD programs and the simulation programs who are saying, oh gosh, are you going to replace us, or are we going to have to compete with you? Then you've got the purchasing groups that are saying, oh my gosh, we need to buy another thing here, all of that. Where we want to live is in between CAD and simulation. So you still output a CAD part, whatever CAD program that you have. And then before you go into simulation, you put it through our optimization engine. That'll say, hey, we can take out half the weight. We can, do all of these other things for you. Fantastic. Then you go into validation as you would normally. So this part of the question is where, a lot of people were getting real hung up on a few items. So I was chatting to some guys that said, hey, are you gonna put simulation out of business? I said, no, you still validate the part. I mean, you just don't have to simulate it 10 times and, change, beam size 15 different steps and then go see what it does. You still use it for validation to make sure that the part works. And then on that same call, they were like, well, I handle accounts that, these are only a couple people. They don't have simulation suites. Can they still use the tool? And I said, well, of course. I mean, how did everybody do engineering before the 1980s? I mean, you just build it, right? So yep. The challenge is never, what people get wrong is the challenge with like these lattices and everything, it's not building it and testing it. It's also not actually simulating it. The challenge is having to do that like 1,000 times. Because you guess some random parameters, you make some random lattice, you test it out. Obviously, it doesn't do what you expected because you just guessed on all those parameters. And then you have to go back and refine. That refinement stage is what costs everybody time and money. And that's why smaller organizations can't effectively use these tools. Because, yeah, it might save you 5 hours of printing, but if you had to spend 100 hours of engineering to get to that 5 hours of savings for printing, it's a real waste of time.
Right. And so you mentioned some of the beam shaping stuff. So I assume this is process agnostic, or do you want us to focus on a handful of printing technologies?
We want to get to process agnostic, but there's a lot of problems with that. The primary one being the processes are so different. Everybody's got their own requirements and special things that are happening X, Y, Z. So we need to make sure that those are accountable. Now, where we start is single machine, single material. But where we want to end is all of the machines with all of the materials. The goal with that is to be able to actually work with the OEMs to do it. I have no interest in buying one of every single machine on the planet. And even if I do, the OEMs are probably better at running them than I am, at least for a while, at least for the first couple of years of this. So just to kind of put this into perspective, for us to build out a single data set for a single structure, let's say it takes around 10,000 parts to actually do. So we'll build 10,000 variations. And
what do you mean a single structure, like a single lattice?
Yeah,
design,
so like an FCC or a BCC or a fluorite lattice, any of those, even gyroid, honeycomb, anything like that will all still be a single model. So let's say a model takes us 10,000 parts of something. It doesn't really matter what it is. The goal is, in order to build another model that's kind of similar, we can build translational models. So let's say on HP Multijet with nylon 12, takes us 10,000. To build one that'll do it for nylon 11, We're hoping that we can do it for maybe 1,000 parts, 10% or even less of the parts. And we can essentially just translate that data back to the original data set. And we say, hey, multiply everything by 2, or something like that, where in broad strokes we can figure that out. And that is the goal, to partner with these OEMs. So we say, hey, you've seen what our tool can do. Let's build it for your process. Provide us with these sample parts. We'll do all of the testing. We'll gather all the data, and then we'll integrate your machine into the process. It'll be a journey. It's going to take a long time. It's going to take a lot of people, and it's going to take a lot of money. But the goal is, instead of one company owning the knowledge of like, hey, I can make this lightweight and strong, we can build essentially one data set that everybody can use and everybody can be productive without having to pay for it again.
Yeah. And so let's talk a little bit about kind of the journey of building a startup, building a company. Like, what are some of the lessons learned that you've taken from working at a GE or Autodesk and some of these big companies and translated it into how you operate your teams, how you operate your labs, and how you think about strategy and kind of the future of the business?
Yeah, that's a great question. And a lot of what I had been doing for all these companies was all purely technical. So it was, can we solve these problems? Trying to start up and run a business is a whole host of other learnings that you have to kind of learn on the fly with a lot of this. Kind of the first one was, I turned down all my job offers after graduation, and I said, hey, I'm going to give this a go for a couple of years. Essentially what I was looking at was 3 paths. I either went and got a job and immediately went to industry. Second option was I went and do a PhD. And this is the third option, is we try and run it. So this is kind of the hybrid option of kind of like a PhD, but I actually get paid. So that was really what pushed me here. First couple of years was just consulting. So between 2019 and kind of 2022 was just consulting for companies I'd worked for before. They knew what I could do. It was pretty standard. And then by the end of 2022, and kind of rolling into the beginning of 23, was talking to some friends about what we were working on. And I was doing some ballistic armor at the time. And they said, hey, the ballistic armor is kind of cool, but, what I really want to know is how the hell you did the math to actually make it work. Because that was the big thing where they're like, oh my gosh, this is like insanity level math that nobody's been able to solve. How the heck can you do that? That led into actually venture pitching. So essentially the question became, in order to build a predictive model, I need a bunch of data. In order to make a bunch of data, I need a bunch of money. And typically a bunch of money doesn't come until after you have customers, unless you have venture capital. So venture was the next thing where it said, hey, if this really does work, then this makes a heck of a lot of sense. And there could be something really big here. We just have to get to the right people. So I said, okay, sounds good. Put together a pitch deck, all of that. 65 pitches later, I probably should have gotten a hint that nobody wanted it, but we eventually found a lead, and that was the 66th pitch that I actually gave, and that was to an investor who had worked in a machine shop in high school. So everyone else was like, oh, just simulate it. Or, the hardware guys we talked to were like, make it print faster, put more lasers in it. Then the software guys that we talked to said, oh, you want to do this analysis? Just simulate it. Like, don't buy the machines and build the parts. And it just so happened that the investor that we talked to was like, hey, well-versed in the digital space, but then also said, hey, this is really hard to do in real life. If this could actually work, it could be really big. And that was something where it was just, again, 65 pitches. I probably should have gotten the hint, but stubbornness prevailed and got us funded. The second piece of all of this is, how to actually do the raise, because it's like, great, we have a lead, fantastic. They're going to give us, a bunch of money to get this thing kicked off. Well, then the second problem became we couldn't get the rest of the round filled. So the next question with that was, hey, if we only have 70% of this round filled, can we still do this? Like, is it still worth starting, or are we not going to be able to make it to that milestone? That was something where, again, the engineering process really helped to build that budget, because there were things that we had accounted for that we said, hey, we're pretty sure that we're wrong on this prediction. So we're going to have a little bit of slack in both the budget and the timeline in order to guarantee that we can hit it. By planning that way, by the time we actually were coming close to running out of money, we actually had product that we could show. And that kind of saved our asses, because we were able to say, hey, you know how you guys thought we couldn't do this? It's actually possible. Please give us money quickly before we run out. um, so the biggest thing that I like to impress on the team here is, everybody is scared for all of the unknown stuff because people don't like to fail. And it's a tough job when 90% of the stuff that you do doesn't work. But what I like to continually tell the team is you won't get better by not trying. You won't get better by not doing it, right? Now, even by doing it, you still might not get better, but you definitely won't get better if you don't do it. And that's where, it is part of the culture here to say, hey, I'm expecting this to take some time and this is going to go through some iterations and some of the stuff is going to work and some of the stuff is not going to work. That's okay. And not only is that okay, but that's also budgeted for. The problem is if we are, not learning and we keep making the same mistakes. So as long as that doesn't happen, we're good. And that's really what's, I think, helping to push forward a lot of the learnings for the team, because pretty much every single thing that we're doing here has never been done before. And like I alluded to a little bit earlier, that results in almost everything that we try not working. And that is a tough thing to do, where you just try 1,000 different lattices and none of them work. Yeah. And that's what we do here every single day. And it takes it takes a very specific kind of person to be willing to beat their head against a brick wall for that long.
Awesome. And so just a couple last questions. So one, what are you excited about in the next 6 months? I know if you read the 3D printing trade online reports and things like that, it's all doom and gloom and this company is going out of business and all that. But from the position of kind of building your startup, launching a product or kind of a beta in June, and kind of what keeps you motivated to kind of keep going towards that 66th meeting or kind of getting to that next experiment, next kind of failure, getting through that?
Yeah. So for me, it's been the last 8 to 10 years of frustration reading the 3D printing headlines, because everybody keeps talking about this new machine or new process or new something. And then they say, hey, this one OEM used it and then they built these 2 parts. And I've been looking at that since 2014, just being like, oh my God, why would you do 1 part for a spaceship that makes it a little bit lighter when I could deploy 1 million parts for a car and, across 1 million different units and then make them all, 50 grams lighter, right? And there's a lot of things there that I continually get frustrated by. What I'm really excited with is, again, we are right on the horizon here of actually releasing the tool commercially, where we're already working with users, already looking for those people who are excited and looking forward to the future. And the goal is, I want to see what people can do when we get this out to all the people that Additive hasn't been able to touch. It's been sweet being able to work with the Additive guys, see the newest machines, the brightest things, and all of that. But let's be real, who's making most of the stuff in the world? It's not the Additive guys. And if we can start getting these capabilities into everybody else's hands, I cannot wait to see what they can build. I want to see what every machine shop in the country should be able to do this Additive stuff. And maybe it's not, 100% as good as a whole dedicated team of NASA engineers, but I expect a machine shop to be able to do 85% as good, 90% as good. They should be able to get progress and be able to say, hey, I could machine this part, but let's take a look at Additive. Let's see if we can do it a lot lighter, a lot cheaper, a lot faster, and a lot more efficiently than ever before.
Right. So last question, more of a fun one. So is there a book, podcast, or anything in that vein or spirit that you would recommend to our listeners as something that had made an impact on how you think about entrepreneurship, leadership, kind of what you do on a day-to-day basis?
So a slightly different approach. I do have a technical background. I'm not coming from business school or anything like that. A really, really good book by Matt Parker. It's called Humble Pie. So it's a collection of stories of where math went wrong. This was where somebody had a slight miscalculation or something like that, and how that cascaded through a product, through a country, through an industry, and caused a lot of problems. That, I think, is a really interesting one, because the obvious stuff is something that you'll find YouTube videos on, if you type it into a generative AI prompt, you'll find those things. All of the normal ones, that's your, honestly, if you read the titles of the business classes, you'll get all of those. Where I think it's really interesting and way more poignant is all the ones that you don't expect, because those are the ones that are going to either get you, or they're the ones that are going to make the difference. For instance, with us, a little bit behind the curtain of all of these lattices is my background is semiconductor crystallography. There's a lot of math there that mechanical engineers never learn because it's an electrical engineering class. That's really, really useful. And what we're finding is by applying a lot of that, we can make these structures a heck of a lot more productive for everyone.
Awesome. Well, Aaron, I really appreciate you telling your story, kind of sharing kind of where you guys are on development of the company and the technology. We're super excited to see where it goes. And if people want to either get in touch or learn more about what you're working on, do you want to just point them to kind of yourself or a website?
Yeah. So our software, our website is vixiv.net, Vixiv. And you'll be able to, the other easy thing is just email me. So I'm just Aaron at vixiv.net, just AARON at Vixiv.net.
Awesome. Sounds great.